And plasticity is, you can think of it as related to, or a physical property, is like pulling on a slider block. So I apply a load of force to that block, and what happens? When I first apply a force, nothing happens, right? This is another classic sophomore physics experiment, right? You probably did these, right? But eventually, you'll reach a critical force at which you exceed the so-called coefficient of static friction, which has physical meaning in geology that we'll come back to later. But once you exceed static friction, you can just keep pulling the material at constant force. Now, what actually happens commonly in common material behavior for true friction, there's a breakdown. So there comes down and drops to a lower value. That's a different physical property. That's not quite the same as plasticity. But nonetheless, the idea is the same. There's a breakdown force, and once you do that, you can allow the material to move. It's simple to quantify. If force is below the critical force, nothing happens. Displacement equals 0. And if F equals F sub C, D can be whatever it wants to be. You can just continue to flow or move with that particular physical property. In a sense, frictional slip is plasticity. It's modeled that way sometimes. But a material behavior that might be familiar to you, it's like this, are metals, where metals can permanently deform. If you take a metal, it has a certain point, it's elastic. But you go beyond a certain point, you'll bend something, and it'll be permanently deformed, right? And there's a yield stress that occurs at that, and that behavior is pretty close to perfect plastic behavior. The difference, the important difference between plasticity and viscous behavior is that, unlike viscous behavior, the smallest load will produce a deformation. In plastic behavior, if your loads are below the threshold, nothing happens. It sits there and stays what it is. But if you exceed that quantity, then the material can deform under a variety of conditions. So one way to think of that is that the material has some sort of inherent strength such that nothing really happens until you exceed that yield strength. And then beyond that, everything's controlled by dynamics. There's a relationship between the forces and the deformation, though, in this particular context, that is not time dependent in an ideal plastic material. Once you reach yield, it's only inertia and things like that control rate, or some rate controlling process is different than that. So there's no inherent rate relationship within it. Engineers often use this as a model for clay, for example. Near surface behavior of clay, which has a yield strength on it. So if you want to know whether that slope's going to collapse, you would use a plastic model to know whether you're below the yield strength, you're fine. If you go above the yield strength, you're dead and you're buried or whatever, right? Now, all of these models, elastic, viscous, and plastic, are ideal laws. Real things don't really behave that way. And this is a good example of one way that you can model a more realistic type of behavior that might be more diagnostic of, say, an earth material by combining the effects or using all three of those different materials. This thing is actually, this little figure, I realize, is backwards. This should be on this side, as we pull on this, right? What would be the effect? So put the spring on this side, you've got a viscous effect, and you've got a plastic effect in parallel, so that neither of these can move until they both move. And then if you put the spring on the front of it, think about what happens if you load this system. If you pull on it, you'll first get the elastic response. So if you're below the critical yield stress for this block, so to speak, all you'll do is have elastic effects. You remove it, it's gone, nothing happens. But if you pull on this far enough, or hard enough, to exceed that plastic behavior, then it'll start to move, and now it has a viscous effect, which will control the rate of sliding on this process, or the rate of deformation will be controlled by the viscous effect. You could plot that on a graph. Well, this is a weird way of showing it. Well, here would be a perfect fluid. This would be equivalent to the displacement rate, or the velocity on this side, versus on this side, which is the stress. This has the effect that the yield stress is here, or yield quantity is here. Usually this would be laid on its side the other way. I think I had it plotted the other way. Didn't I have force on one axis? Doesn't matter. But there's a yield criteria, and then once you exceed the yield, then it's controlled. The rate is controlled by the viscosity effect. That's probably a better model for earth materials, the way we think, and we'll come back to some of that a little bit later. But that's probably a better model for how earth materials deform, because we can see that in kind of rock behavior, that rocks can sit there kind of doing nothing for very long periods of time, but if you exceed certain values, then they can start to deform very rapidly. And there's a bunch of different ways that you can do that. Maybe I should try this one. You can try that video too. There's a bunch of them there actually. And I thought about coming here and playing, have you ever heard of cornstarch slurries? That's what that one's about. Follow that one. There's all kinds of cool videos on that one, like people shooting a bag of cornstarch slurry. And it's kind of fun to watch. But this one is an illustration. I think this is actually paint. And a material that has this kind of behavior that you're familiar with is paint. It's designed that way because if paint were a perfect fluid, if it were a viscous, Newtonian viscous fluid, what did I say was the main property of a fluid? If you apply a load to it, what happens? Always
flattens out,
right?
yeah.
So you put paint on the wall, it's always under gravity. If it were a perfect fluid, what would happen to it?
Puddle on the ground.
Wall. And so instead it has this kind of physical property. It's got a yield strength such that when it's not deformed under lower forces, or doesn't have much of a load applied to it, so when it's sticking onto the wall, it won't deform. But if you deform it quickly, or you push a lot of force on it, it acts like a fluid. And that produces, if you watch that video, you can see some of the weird effects that non-Newtonian fluids do. Like there's a strange effect, like you stir it, and the material climbs the wall of the stirring rod. It'll climb the stirring rod because that's a lower stress state, and it just kind of climbs up the side. Or if you stir it inside of a body, it'll climb the sides of the. You might have seen this with paint. When you stir it, it does this weird thing, like it'll climb up the side of the paint jar or the paint bucket. You may not thought about it, but it shouldn't really do that. And it has to do with the way it's flowing, and it's just this weird physical property. But those are called non-Newtonian or non-linear fluids, and most earth materials are thought to be something of that particular sort. But okay, so what's the point of all this? First of all, the point of this was to illustrate that there is a relationship between the deformation of a material and the forces that are applied to it. And you can describe that. That's the way that's quantitatively modeled, is through those connections. So if you know something about viscosity of material, or you know its physical properties, you can make a model. These days with fancy numerical modeling programs, you can describe deformation or give it some physical property, and you can model a geologic process. But to do that, you have to understand the connection of those through that rheological parameter, give it some value, and that's the part that is not as easy. But the other part of this was related to the fact that we talked about strain, and I showed you that strain was a quantity that wasn't force. And in all these experiments that we talked about, this is where physicists always lie to you, right? Or just like the mathematicians lie to you. It turns out that plot you make of force versus displacement, or force versus displacement rate, is really not plotting the right quantity. Because when you're plotting force, that's a vector quantity, and that's a one-dimensional problem. What it is a one-dimensional generalization of the property we want to talk about. And the real property we want to talk about is a quantity called stress. And here's always my favorite example of an illustration of why that can't be right. I'll give you two examples. Here's a rubber band. I found it. I couldn't find one, so I stole it from Pam about 20 minutes ago. Here's a rubber band, right? It's a perfect example of elastic behavior. So I could take this and I could do my little physics experiment in which I measured the changes of forces as I take that quantity. And this is the same material in which, and I can measure that quantity. It gives me a force versus displacement. And that's supposed to be a material property, right? Yet, if I were to take the same rubber band and fold it over, and do the same experiment, I could have handed you all rubber bands if I'd had 30 rubber bands. But I do the same experiment. It's not the same, is it?
Mm-mm.
It's going to be much harder.
Resistance should double.
What if it's a physical property? Why wouldn't that be the same? Right? That's the lame part of the experiment. Then you say, well, then that can't be set up right. There's something wrong in the experiment. Here's another, so I already said that one. So why is it different? And the answer is that the force is distributed over a different volume of material. I doubled the volume of material over which I applied the force. That is an illustration of why force is not the right quantity. And it's related, in this case, then somehow to volume within the material, or the mass of the material. So there's something more involved. Here's another example. The same exact same sort of little experiments you do, right? The other one is the plastic model, which we just talked about, the sliding block, right? And this one always bugged me, right? Why the heck? That doesn't make any sense, right? They always gave you the statement you did that the sliding velocity, or the sliding force, was proportional to the weight of the block. That was what they, in the little experiments, always say, right? But they also always told you, well, it doesn't matter what the block looks like. There's a big flat thing, or a big tall thing. The result of the experiment is the same. And you can do this. I mean, they lots of times do this as an experiment, right? But then they also tell you that that's a material property, the coefficient of friction, right? But you have to ask yourself then, well, that doesn't make any sense either, right? Why would it be the same if I had a big flat thing versus a big tall thing? That's a physical property. Why would that have that physical property? And what's wrong with that experiment is exactly like the other one. It's not the weight of the block, it's the forces that are applied over an area. In this case, it's the contact area between the two different blocks across which you're making that particular measurement. And we'll talk about this shortly, but what that really means is the proper law for frictional sliding has to do with normal stress directly proportional to shear stress across the boundary. And we'll talk about that when I go to specifics of that. But the bottom line is that's an illustration of an area concept, because the surface area varies. You have the exact same weight, but the forces are distributed differently across one area versus another, and so you get the same effect because they cancel out. So the quantity, I'm doing on time scale before I can get here. Okay. Stress, like strain, or strain rate, is another one of these quantities called the second order tensor. But stress, in a way, is a little simple. In one respect, is a little simpler to understand as sort of a mathematical concept. I'll see if this little link at least works. You can follow this on your own.